G-TAD, subgraph localization for temporal action detection. Motivation and G-TAD overview. Based on the motivation that video context does not only include temporal context, but also semantic context, G-TAD seeks to take advantage of both kinds of context by use of graphs. It casts temporal action detection as a subgraph localization problem. It models all snippets in the video as nodes in the graph, snippet-to-snippet correlations as edges, and actions associated with context as target subgraphs. G-TAD is comprised of two components. First, GCNext block. It learns the features of each node by aggregating its context and dynamically updates the semantic edges in the graph. Second, SD-align layer. It represents each subgraph as a feature vector. Overall, G-TAD adaptively incorporates multi-level semantic context into video features. It finds effective video context without extra supervision, and it achieves state-of-the-art performance on two detection benchmarks. On ActiveNet 1.3, it obtains an average MAP of 34.09%. On TMUS 14, it obtains 51.6% at IOU 0.5 when combined with the proposal post-processing method. G-TAD details. This is our graph formulation of a video. We use a graph to represent a video. We take each video snippet as a node. We take snippet-to-snippet correlations as graph edges, and we formulate snippets associated with context as target subgraphs. This is an overview of G-TAD architecture. The input of G-TAD is a sequence of snippet features. We first extract features using BGCNext blocks. Then we feed the extracted features into the SD-align layer to represent each subgraph as a feature vector. Finally, the localization module scores and ranks the subgraphs for detection. This is a GCNext block. It gradually aggregates both temporal and multi-level semantic context. Semantic context, encoded in semantic edges, is dynamically learned from features at each GCNext layer. This is SD-align layer. Subgraphs are defined by set of anchors. SD-align layer represents each subgraph as a fixed-size feature vector in the Euclidean space. The localization module scores and ranks the subgraphs for detection by three fully connected layers. Here are the details of the GCNext block. The input feature is processed by temporal and semantic streams with the same cardinality. Both convolution streams follow a split transform and merge strategy with 32 paths each to increase the diversity of transformations. In this figure, black and purple boxes represent operations in the temporal and semantic streams respectively, darker colors referring to graph convolutions, and lighter ones one-by-one convolutions. The numbers in each box refer to input and output channels. The output of the GCNext block is the summation of both streams and the input. Here are the details of the SD-align layer. It extracts subgraph features based on both GCNext features shown on the left and semantic features shown on the right, and concatenates both subgraph features as output. The dots on top represent the extracted subgraph features. On the bottom, the dots represent graph nodes. Gray lines are semantic edges, and the orange zones are subgraphs. When using the GCNext features, the order of nodes is preserved in the final representation. For the semantic features, since they are computed using the neighbors, each entry in the subgraph feature essentially corresponds to multiple semantically correlated nodes in the graph. Experimental results. These are the action detection results on ActivityNet 1.3 and TUMAS 14. On ActivityNet 1.3, we obtained an average MAP of 34.09%. On TUMAS 14, we obtained an MAP of 51.6% at IU 0.5 we combined with PGCN. On both datasets, we reached the state-of-the-art performance. Here we provide some ablation study results on GC-Next and SG-Align components. We do this by disabling different functionalities of GC-Next and SG-Align in G-TAD for action detection on ActivityNet 1.3. We can see the effectiveness of our design in both components. This is an illustration of semantic graphs and context. Given two untrimmed videos, the one on the left and the one on the right, we combine action frames of one video with background frames of the second to create a synthetic video, which is in the middle. The synthetic video, therefore, has no semantic context. As expected, the semantic graph of the synthetic video contains no edges between action and background snippets. Here we visualize some videos for action detection. The green areas refer to the ground truth actions, and the orange arrows represent our predictions. We can see that our detections align with the ground truth very well. Here are some qualitative results. The frames in the red boxes are the ground truth actions, and the orange arrows represent our detections. We can see that our detections align with the ground truth very well. Action background semantic edge ratio versus context amount. In the scatter plot, each purple dot corresponds to a different video graph. Strong positive correlation is observed between context amount and action background semantic edge ratio, which means we predict on average more semantic edges in the presence of large video context. This demonstrates semantic graph evolution during G-TAD training. We visualize the graphs of the semantic stream at first, middle, and last layers during training epoch 0, 3, 6, and 9. The edges at the first layer are always the same, while the graphs at the middle and last layers evolve to incorporate more context. Thank you for watching.